It. And it's a great pleasure to have today Tom Melia, who is a assistant professor at Kavli IPMU. And just briefly say a few words about his career. Tom got the PhD from Oxford, and then he did a postdoc at CERN and UC Berkeley before joining Kavli IPMU 3 years ago, right? And that Tom is has expertise, a very wide range of expertise, impressively wide range of expertise in theoretical physics, particle physics, starting from mathematical aspects of QFT and phenomenology, particle phenomenology, and the dark matter phenomenology. And today he will be talking about EFTs and beyond standard model physics. Right. Please, Tom, please share your slides and
yeah. Thanks for the introduction and for the invitation to give the talk. So let me see, this shares, right?
Yes, all good.
Okay, good. Great. So the title of my talk today is going to be EFT asymptotics and the fate of the standard model EFT. And there's sort of there's going to be two main parts to this talk. So the first main part, I'm going to talk about the standard model as an EFT. And then the second part, I'm going to talk about growth or asymptotics. And by growth, what I mean is the growth of the number of measurements or the number of operators you can make in the standard model EFT. And they'll have sort of slightly different flavors, these two parts of the talk. So the first part will definitely be aimed towards more LHC pheno. And then the second part will be based on a recent paper of mine with Sridhar Pal, who's a postdoc at Princeton. And this is definitely not pheno, the kind of numbers of measurements, possible measurements or numbers of operators you might try and constrain in the standard model EFT is going to be astronomically large. So it's not a phenomenological question anymore, but it's more as an analytic probe of EFT and what we can learn about EFT from studying the growth of operators in EFTs. And there's sort of connections to looking at entropy or the high energy states of a theory and studying these analytically. And there are many famous results in 2 dimensions, looking at, especially with dualities, to look at dual theories and compare the entropy of a CFT in d^2 to the entropy of black holes in d^3. So that's going to be the flavor of the second part. And then for the first part, let me start and let me go. I'm going to give quite an introductory talk to what the standard model as an EFT is and how it's used at the LHC. Okay. So let me start with a plot of this. This is a plot of standard model production cross-section measurements. This is an atlas plot. And along the x-axis here, you have a sort of list of the particles of the standard model. So electroweak bosons, WZ bosons, photons, top, anti-top, and then various combinations of them. And on the y-axis, there's the cross-section, which is the measure of how often you expect one of these particular combinations to be produced in proton collisions. And there's a sort of chromatography here. This chromatography subdivides these bins, sort of the Z boson production, for instance, here in association with QCD jets of particles, or this column here of the Higgs boson further subdivides how the Higgs boson subsequently decays. And there's 2 types of things that are plotted on this plot. One is a theoretical prediction, which is these gray bands here. And the other is experimental measurements. And these are the pink bands with errors. And you see this wonderful agreement between experimental theory. And just to sort of zoom in on this is a particularly important column for the Higgs boson we discovered at the LHC. And so just to give you a kind of Feynman diagram of how this is working, you have proton-proton collisions. There's some gluons coming in here to create a Higgs boson, and then this particular measurement here is when the Higgs boson decays to 2 photons, which are then seen in the detector. But as well as measuring all these standard model processes, the LHC is also searching for physics beyond the standard model. We know that it exists, and history and aesthetics have sort of pointed towards our seeing at the LHC. And there are two ways that you can look for new physics at the LHC. The first is direct searches for new physics. So you directly produce the new particle. In that case, you add another column to this plot, and you measure a direct production of a new particle. There's a second way, and that second way is more indirect, this is the way that I'll be mainly talking about today. So just to give you an idea of how many of these events that we have. So this is converting the cross section, the predicted, how often you're going to produce this event, into an actual number of events that we'll see at the end of the LHC. So you can see that this is the number of events of each type produced at the end of the high luminosity LHC run. So there's sort of order 10 to the 10 of some of these events down here involving the production of electroweak bosons. There's a lot of data to work with and a lot of potential. And so this second way of searching for physics has parallels with CMB measurements. And in some ways, you can really consider this sort of list of particles. These really are the CMB photons of the LHC. The parallels, I think, actually run kind of deep. Similarly, the LHC is giving you a window into the early universe, a much earlier universe than the CMB. And there's this idea that you can do precision measurements. These experimental measurements are very precise, and you can compare them with precise theoretical predictions. And there's a whole industry of producing very precise theoretical predictions for these processes to be produced at the LHC. And there's also a sense in which this search for indirect search for new physics is a search for these anisotropies in the standard model measurements, in the same way as you look for anisotropies in the photons of the CMB. And in fact, this whole thing can be made rather precise, and this sort of analogy can be drawn to a point where you can actually define a power spectrum of the standard model, and that was the subject of a paper that I had last year. Actually, the two papers. I should have another reference. But this is not going to be the subject of my talk today. I'm going to talk about a slightly different thing. But if you're interested, you can check that out. But it's quite a useful thing to keep in mind. And so this is where EFT comes in. So EFT sort of makes this whole story precise. And EFT more broadly is a very universal concept. It has diverse applications from condensed matter physics to cosmology. It's really the way in which we like to think about doing physics. You parameterize the relevant degrees of freedom and work with those. And that's the kind of concept of using EFT. I'm focusing today on relativistic EFT, which is the framework in which you can search for new physics at colliders like the LHC. And it's really this ability to sort of parameterize what we don't know that makes it a very natural way to quantitatively discuss these anisotropies or potential anisotropies that may exist in the LHC data. So it's a quantitative framework. And just to give you a bit of historical background, so the existence of the W and Z bosons of the standard model was in fact inferred already from the fact that beta decay happens. Beta decay being an interaction between a proton, a neutron, an electron, and a neutrino. So this is the low energy side of things. This is the high energy side of things. It's really a W exchange between quarks and the leptons. And it proceeds because you can borrow this amount of energy to produce a W boson for a very short amount of time. So there's a way in which this low energy process can proceed even though you don't have the energy to actually produce this W boson. And EFT says, well, what you do is you take the low energy theory, so in this case, the protons, neutrons, electrons, neutrinos, and you make a coordinate chart out of them, or a basis, and you write down all possible interactions between these low energy particles. And so here, we typically think about this as a Lagrangian. Here, there's a terminal Lagrangian that you can make by contracting. These are now fields, really. These PNs stand for fields that describe these particles. But you just contract their free Lorentz indices in some Lorentz scalar, and it sits in a Lagrangian. And then you can go and compute things with this Lagrangian. And the standard model EFT works in exactly the same way. So this is the EFT that's relevant for these new physics such as the LHC. And instead of protons, neutrons, electrons, and neutrinos, you now have all the particles of the standard model: Higgs, tops, gluons, bottom, photons. And again, all you do is you make essentially a coordinate chart out of all of these particles. So you write down all possible interactions that they can have. So for instance, there is interactions, these are polynomials and these particle operators, and also derivatives that can act on them. And they have to be Lorentz invariant. So for instance, you could contract the indices of a Higgs field, the top field, the W field, and the bottom field in some way to make them Lorentz invariant. They also have to be gauge invariant. They have to respect the gauge symmetries of the Standard Model. And you can think of this as like a coordinate chart that can be, obviously there's an infinite number of measurements you can make. There's an infinite number of derivatives you can apply and sort of tie up the Lorentz indices. And so there is an infinite number of operators or interactions you can write down, but you can organize this chart using just dimensional analysis. And so you know the fact that the Lagrangian has to be dimension 4 tells you that you know the canonical mass dimension of each of these fields and the mass dimension of the derivative. So you know that when you start joining these fields together, the more you join, the higher mass dimension this has. And so it has to be suppressed by some large energy scale. And this is the scale at which the cutoff of your EFT is, some high UV scale. And so just to introduce some terminology, the operators that are suppressed, or operators that have mass dimension of 5 are called mass dimension 5 operators, and they're suppressed by 1 power of this large scale, and mass dimension 6, and so on. And these are the sort of coupling parameters. And this looks a lot kind of CMB-like. So you can imagine the Standard Model Lagrangian as the isotropic piece, and then these terms as little anisotropies on top of that we're trying to measure. So that's the kind of picture to keep in mind. Now the physics is in the coefficients, these C's, these Wilson coefficients that we would like to measure and constrain by LHC. And the operators themselves, well, there's some sort of choice of coordinate frame, if you like. And so there's many different coordinate frames that you can choose. There's many different operator bases in existence, a frightening number actually. But they all describe the same physics. So the islands are what they are here. They just look different in different charts. And in some sense, what I'm going to be talking today about is actually the dimension of these charts. These charts are all two-dimensional here, and I'm going to be interested in how dimensional these charts get. That tells you how many operators there are, or how many measurements, what dimension space you're trying to make measurements in at mass dimension 5, mass dimension 6, and so on. And to give you an idea of how this works in terms of LHC pheno, so this is again this Higgs process. So one of these operators can affect the way that the Higgs talks to the 2 photons, and so it can affect the decay of the Higgs into 2 photons. And so this is the plot that I showed earlier. Let me zoom in. So there's some measurement that is made by the experiment of this cross section. There's some theory. The Standard Model, the isotropic term, gives you some theoretical prediction very precisely now. And you can use this measurement, the fact that you measure this, and the Standard Model theory, the isotropic term giving you this, you can quantitatively go and work out the effect of these anisotropies and how much they would change this number by. And in doing so, you can constrain or measure, but in actuality, these all sit at 0 with some error bar, constrain the Wilson coefficients. Constrain these parameters C's. Okay, so all of these sort of come out of the measurement of this vertex. And there's many, there's this whole spectrum of things you can measure at the LHC, and so there's many different coefficients modify different processes. So, for instance, there are coefficients that modify top decay, and they can also be constrained in this way. And this is going to form a very important part of the LHC program for the next decade or 2. So what is the problem here? So it turns out that this writing down the Standard Model EFT is actually kind of complicated. And it's had a complicated history that stretches back to the 1980s, 1986, where, well, so the mass dimension 5 terms were written down by Weinberg, and then mass dimension 6 terms, well, there was a basis that was first written down by Buchmann and Weiler. This was actually an overcomplete basis, and this was noticed in 2010. And since then, there have been bases or operators constructing the basis at higher mass dimension, at mass dimension 7 or mass dimension 8. And here, I should say that the 2 different lines here, the 2 different sort of numbers that I'm connecting here, when you consider the Standard Model with 1 generation of fermions, or if you consider the Standard Model with 3 generations of fermions. And so there are red arrows and green arrows on this plot, and the red arrows are results that were incorrect in the literature, and the green arrows results that were correct. And so this kind of tells you that it's a tricky business because it's a 50-50 split. And so one of the tricky things about this is because when you write down all the operators, they're not actually all independent. So you can write down everything that's Lorentz scalar and gauge singlet, but there still exists some relations between these operators. And actually, the particularly tricky ones are relations called integration by parts relations. I will come back to those in a few slides' time. But so one of the things that in a series of papers that I did with my collaborators is to really systematize this process of at least enumerating the operators in the standard model EFT. So systematically counting how many independent operators there are modulo these tricky relations as a function of mass dimension. And so you see here we could push all the way up to here. I stopped at mass dimension 15. And the key to doing this is to consider the full basis, not just to focus on these phenomenologically important terms down here. These terms, of course, are the ones that come with less suppression by this large scale. So they're going to be the ones that should, not in every case, but in most cases will affect your experiment the most. These ones are going to be very tiny. But if you consider the entire basis, you start to see patterns emerge, and there are connections to conformal representation theory, commutative rings, and graph theory. And I will tell you about one of these connections just to sort of paint a picture of how broadly we attack this. And so this is the picture that I want to paint, just to give you an idea of how we came to some systematic description or a systematic way of enumerating these operators. So when you write out all of the operators, so you really consider the full possible operators that you could write down without worrying first about these redundancies, you start to notice patterns. And so you start to notice that there's some action that you can take on one operator that turns it into another operator. And then you notice that this operator is again related to another operator by the same action. There's something that you can apply to these operators, some operator in fact, to take you between them. And so this sort of acts a little bit like a comb. You can tease out operators that are connected to each other just by this comb operation. And you can form this sort of hair that sort of threads its way through this infinite space of operators that you've written down, or that you're considering at least. And then as well as this comb operation, there's also a back comb, an anti-comb operation. So you can back comb the hair all the way back. And in fact, you back comb here, I've labeled this operator 9, you back comb it again, you get another operator, I've called it operator 4. But then you back comb the operator 4 again, and you annihilate it. So it stops. So this process terminates. You've sort of reached a follicle of the hair. And this should sort of remind you of exactly what happens when you construct states of the harmonic oscillator using creation and annihilation operators. So you have some state, the vacuum, and then you can apply a raising operator to put in more, to have one occupation number, two occupation, three number, and so on. You can raise up the states in this way. And there's also the backcomb operator, the annihilation operator, this A here. This A brings you back down this tower of states until you reach the state with no quantum in it, and then the A acting on that state annihilates it. And so it's the same thing here. And again, this is also infinite dimensional, and so these hairs are infinite dimensional, but they have one sort of singled out special operator. So the idea is that you can apply this comb again and again to all these operators and sort of start to organize them by this action of this comb. Now let me tell you what the comb operation is. It turns out the comb operation is just a derivative. And so taking you from here to here is just purely acting a derivative, total derivative on this operator. So you start off with operator 4. This tells you that operator 9 is just a derivative acting on operator 4. And if you have an operator that is a total derivative, it just gives you a zero contribution because it just integrated by part. It just tells you it lives on the boundary and it's assumed to be vanishing theory. So any operator in your Lagrangian as a total derivative doesn't affect your physics. And this is why this is so important, because doing this combing operation really organizes the integration by parts, these IBP relations between operators. I told you were these tricky relations. Now let me tell you sort of why they're tricky. So it's very clear that if you have three operators, A, B, C, and you take the total derivative of these operators, it's going to be 0. This thing is 0, just because this is a total derivative. But if I apply the product rule, put this derivative acting on A plus derivative acting on B plus derivative acting on C, this gives you 3 other operators that sit somewhere here. And it's not obvious just by staring at them, at least in the general case when you're trying to do this. It's not obvious that these 3 should combine in a particular way to give you a total derivative. And so you had to sort of, that was the trickiness without systematically first combing them out. And so these operations are actually the generators of a symmetry group. And the symmetry group here is the conformal group. And so the back coma is the operator often labeled K. It's the special conformal generator. This is what takes you back along the comb. We want to count only the operators that are not total derivatives. So we're only interested in operators that live at the follicles of these hairs. And so we're only interested in the operators that are actually annihilated by this generator. These operators are called conformal primary operators. And so we're interested in counting these conformal primary operators, or if you like, these follicle operators. And that will tell us how many independent operators there are and organize all these integration by parts relations. So these hairs that we're combing out by these operations are representations of that group. So we've sort of identified the fact that the conformal group has something to do with this operator problem, or this EFT problem of writing down all operators in the EFT. And so we want to now count, if you like, the number of hairs, so counting representations of that group. As soon as you've identified a group and you care about counting representations, you can now turn to some old 19th century mathematics and mathematics of invariant theory, where this kind of problem was all worked out. And in fact, this invariant theory was founded by Hilbert of Hilbert space. So there exist systematic procedures to count representations given a group. Okay, so you can construct a sort of black box to do this using these tools. And the sort of inputs to this black box are the particles of whatever theory you're interested in. Here I'm talking about the standard model, EFT. So these are all the particles of the standard model. They sort of come with their Lorentz representations. They come with their representations under the gauge groups, whether they're in the fundamental representation or they're singlets or they're in the adjoint representation. And then you put in the mass dimension that you want, because you can keep track of all these fields' mass dimension. And you put them into this black box, and out this black box spits out something called a Hilbert series. So this is a sort of a Hilbert series black box, and the Hilbert series is a list of, these are now variables. These should not be seen as fields, but these are variables and they have their names that are the same names as the field. So H is a variable that corresponds to the Higgs field. Q is a variable that corresponds to the quark field, and so on. And so this is some sort of polynomial in the variables that have names after the standard model fields. And this polynomial tells you the coefficients in front of each of these terms, tells you how many independent operators that you can write down in your Lagrangian, how many independent operators there are with this particular field content. So you see here, for example, there are 2 on this term. This tells me there are 2 possible operators I can write down if I take 2 Higgs fields daggered, and 2 derivatives. So these derivatives, this is again just a variable that represents the derivatives. It's not really acting. It doesn't give you this Hilbert series doesn't give you the information of how it acts, but it tells you that there are 2 operators that you can write down that are independent. That's very, very useful information. And so if for example you set all of these variables to 1, you're going to count this sum, this polynomial becomes 1 plus 1 plus 2 plus 1 plus 1 plus 2, and so on. And so you sum over the total number of operators. These are all the operators at mass dimension 6, I just said. So you're summing over all operators at mass dimension 6, and that gives you a number 84, and this is the number 84 that appears in this chart that we made, this systematic way of doing it. And so you can do this again and again and again, moving up in mass dimension. This black box will spit out these long polynomials, and you can sort of set all the variables to 1 and reproduce this plot. But there's more information than that there. As you see, there's sort of fine-grained information here about how many operators of each type there are, and that's very useful if you actually want to go and write down these operators and start working out how they affect your physical predictions. Okay. So there's something that people often ask me straight away when they see this plot is, how quickly this number grows. So you start off down here at mass dimension 5, and there's 2 operators. Then just focus on the case where there's just 1 generation of fermions. So there's 2 operators here. There's 84 operators in mass dimension 6, which already kind of sounds like quite a lot. And sort of mass dimension 6 operators are what the LHC is currently constraining, and there are 84 of them, and there's an 84-dimensional space that you're trying to look for deviations from the standard model, and it's already difficult. Mass dimension 7 is this little drop, it's 30, and then mass dimension 8, so the sort of the next to leading order correction to the kind of things that you're looking at for the LHC, and indeed the kind of contributions that go like dimension 6 squared. Dimension 6 come with a 1 over lambda squared suppression. Dimension 8 operators come with a 1 over lambda to the 4 suppression. There's 993 of these, so there's an awful lot. But by the time we get to mass dimension 15, in the full standard model EFT, there's enough operators such that, well, in 2017 at least, everyone in the world could have had a single operator. In fact, this is the world population within a percent. There's now it's not, so now you have to go one dimension higher to give everyone in the world an operator. But in 2017, this was the case. Okay, so that kind of brings me to growth. So I want to talk a little bit about why it is that this grows so quickly. And actually, I want to talk about the details of how this grows and exactly how this grows. So this brings me to the second part of my talk. I guess I could stop here and ask for questions at this point. Is it a good stopping point? And just to reiterate this, what I just described here, this black box, and we're going to look inside this black box a little bit in a minute. But this black box is some analytic tool, if you like, that was introduced to study EFTs, some aspect about EFTs, at least some notion of the degeneracy of operators as a function of mass dimension. So it's all the growth of the number of operators in the EFT. And I'm going to talk about that in more detail now. Okay, so before sort of looking into that black box, I'm going to try and just intuit why this growth is so much. I mean, because I often do get this question, like, why is it growing so fast? Why is it this exponential? This is a log plot, right? So this is an exponential growth. And so to do that, I'm going to introduce a simpler EFT, which is a Lego EFT. So consider these Lego blocks, these 2x2 Lego blocks. And the game is the following. How many distinct ways are there to combine these 2x2 blocks? These are all of the same color, so these are sort of indistinguishable from each other, if you like, just to make things easy. But that means that if I take 2 blocks and I sort of put them together, if I can rotate these I do it 2 different ways, but I can rotate them to look like the same, I'm going to just count that as one distinct way of joining these blocks. So when there's one 2x2 block, there's only one possible way in which you can do this. It's trivial. Okay, so this is the question. This is, in fact, I wonder if we could have a poll now. So if you have 2 2x2 blocks, how many distinct ways are there of putting these together to make distinct configurations? Oh yes, it works.
Yeah.
So hopefully everyone can see a poll. This is the Ask the Audience part of the talk. So everyone can see a poll with some multiple choice answers. And if you can put in your answer, now we see how many people are paying attention.
Listening.
another result in. Did the results come in actually?
Yeah, I mean, we have 50% participants already in. Anyone else want to?
people are maybe either thinking very hard about it, or maybe we could just move on with the results.
Stop the poll, right?
Mm-hmm.
Okay. Okay, and share the results.
Wow. Okay. So 22% said 1, 33% said 2, 11% said 3, and 33% said 9. Okay. So the correct answer is 3. So these are the 3 ways in which you can combine them. So you might think that you can, well, you can sort of arrange this block here, you can put it over to the other side, but then you could always rotate that back into the same configuration. And so there are 3 ways in which there are sort of distinct blocks that you can hold in your hand. Okay, and the point of this EFT analogy is to say that this is really a lot like building operators in a Lagrangian. So you can consider one of these Lego blocks, you consider each of these sort of these outy bumps to be like a Lorentz index, so mu, rho, sigma, and each of these innie bits here to be another Lorentz index here. And so when you join one of these sticky outy bits into an innie bit, it's like contracting a Lorentz index. And so this configuration of blocks looks like I've taken the operator O, mu, rho, sigma and contracted all the Lorentz indices in this way. This configuration has sort of 4 free Lorentz indices. I've just contracted 2 of my indices together. And this one has 6 free indices in the sense I've just contracted 1 index together. So it's really a very similar type problem. So there's one more ask the audience question, the poll question number 2 that maybe we just do quickly. And that's to how many blocks, how many ways do you think it's possible to combine 3 2x2 blocks? Okay, so I'll let the poll.
Yeah, how do I launch this poll? No, this is the same one.
No, that was the original one.
Yeah.
Well, never mind. Everyone can make up their
Sorry, this is my fault, I guess.
That's okay. No. Everyone can have their own guess. So oh, there we go.
Oh yeah.
Okay, I submitted my answer, but I So I should say I invented this game while on lockdown. No, actually, it was before lockdown. Even playing with my sons. So there was I was really doing this, and I was sort of tired, and I had a new kid at the time, so my mind was like not working as sharp as it could. And it took me a long time to convince myself of the answer to this problem. Well. Maybe you can stop the poll and I should move on. Okay, decent spread again. So depending on how many people voted, at least well, I know I voted for the correct answer, but that's the results of the poll. The correct answer is actually 31. So there's actually quite a large number of ways in which you can combine these blocks, and so you can start to really intuit, get a feel for how fast these ways in which you can combine blocks grow, similar to the ways in which you can combine operators to form operators that can sit in a Lagrangian. And so in fact, I was actually really excited when I discovered this game of Lego, because I thought this feels, there's probably a Hilbert series where you probably solve this problem and write a letter to the Lego company. But I typed in the sequence into the online encyclopedia of integer sequences, and I guess unsurprisingly there was an entry there that someone had done this, and so they had enumerated the number of ways in which to combine these Lego blocks up to Lego block dimension 11, in fact. And so this is the growth, but you see it's a very similar pattern to the standard model EFT. And so just for the Lego block problem, if you have 10 Lego blocks, there's enough ways to combine them that the projected world population 2057 there's enough for every person to have their own individual Lego combination made out of 10 blocks. So it's really, really amazing growth. Okay, so now let me ask this question, why growth? So I said at the start, it's not going to be for Pheno. Clearly, this is too many operators to constrain. But another way of thinking about EFT is that it quantifies all possible measurements that you could make in a scattering experiment. And so in some ways, what you're doing is you're quantifying all possible S matrix elements that could be measured, or writing down all possible entries of the S matrix. And so this asymptotic growth, studying the asymptotic growth, is another is one way of thinking about it is some analytic probe of the S matrix. And the S matrix theory was born in the 60s, around the time of QCD, and so the analytic properties of the S matrix have been well studied, and a lot of those ideas really were key to inform sort of modern amplitude ideas that have enabled the precision on the theoretical predictions for LHC processes, especially involving strong QCD. And then much more recently, there have been attempts to sort of bootstrap the S matrix, taking ideas from the modern CFT bootstrap and apply them to bootstrapping S matrix from sort of first principles. And so looking at the S matrix analytically is of intrinsic interest. Now, this is not looking at the actual S matrix itself, it's looking at something much simpler. It's talking about these Hilbert series, and they're just sort of counting the number of possible measurements, the number, like the basis for the S matrix. But this also tells you something about the theory, in the sense that it gives you, when you look at the high mass dimension elements, it's telling you something about the high temperature behavior of the theory, in particular the entropy of the high energy states. So there's famous results for this in CFTs in t is equal to 2, but much less is known in t greater than 2. And so this is going to be the focus of the following, is going to be in theories in greater than 2 dimensions. Okay, so let's look inside this black box. So we can start by just considering the partition function of the free theory. So if I have some theory, some quantum theory, it has some spectrum. So these are the energies of the theory of the states, and these are the delta n's. And then each energy has some degeneracy. We call that an. So I can write down the partition function in this way. Now the Hilbert series, this is the counting all possible states, all possible operators. Well, state. I'm going to use states and operators sort of interchangeably here. I'm allowed to do that because I'm actually going to be talking about free theories, and free theories I'm talking about CFTs, and so there's a state operator correspondence. So I will use those words somewhat interchangeably. But so the partition function counts all states. A Hilbert series counts Lorentz singlets, and so there's some other coefficient an0 that counts the degeneracy of just some subspace of this full space, and these ans are indeed these numbers that we found here for the standard model. So for instance, for n is equal to 8 here, an will be 993. Okay, and I said this about the state, the operator state correspondence is just leading to my language that I use. Okay, so we will continue to work with this full partition function in the following. I mean, everything that I say can now be said for the Hilbert series as well. It's just simpler to write down the formulas, considering all operators, not worrying about the projection down to some singlet sector. I'm going to use variables q here. If I set q is equal to e to the minus beta, this looks much more familiar type of partition function. Beta is the inverse temperature, one of the temperature. And we're going to care about the growth of operators as the asymptotic value of these operators. And this is what you get if you take this partition function and you send either q to 1 here, or that means in this beta variable you send beta to 0, because then you get just the sum on n of an, all these coefficients, and that's always going to be dominated by the high end tail of this sum. And this is related to the free energy and indeed the entropy in the following way. So this partition function is just e to the minus beta free energy. And this can also be written in a slightly different way. You can write it as some integral over some operator density. So here I've used these coefficients that exist only at integer. We know that the spectrum is actually just exists with these gaps in between them. Is only defined at integer values. But just sort of brushing that aside and imagining some smearing that you could do, you can introduce an operator density rho here. And this rho is nothing more than essentially the entropy of the theory. Okay, and we're going to be interested in how this rho grows, this operator density, which is the same as saying this, how these ANs grow, how their growth goes. And you can invert this formula here. So we know we're going to be constructing these ZQs, and you can invert the formula for rho just by taking the inverse Laplace transform of this. And so rho is given by this expression, the inverse Laplace transform of the partition function. And we care, as I said already, about the beta goes to 0 limit. So this gives us the growth of operators as the mass dimension, scalar dimension delta goes to infinity. So now this is kind of looking inside the black box. What does this partition function actually give? This is, I said this is basically a Hilbert series. A Hilbert series just restricts to some subspace of this. But so how do you actually go about writing this down if you didn't know what these ANs were in the first place? And so this goes back to a paper of Cardy's in 86. So let's just consider free scalar field theory in D space-time dimensions. So the scalar has some dimensions. This is actually slightly bad notation. This delta has nothing to do with this delta. Delta 0 is just a term for the canonical scaling dimension of this scalar field, but it's d minus 2 over 2. You get this just from the kinetic term. So there's a term with a d mu phi squared, and you know that the mass dimension of the derivative is 1, so you can work out the dimension of the scalar field. So in 4 dimensions, this gives you a mass dimension 1 field. Okay, and this partition function is given by it has the following form. And so this first term here, if I expand this, it gives me 1 plus q to the del 0 plus q to the 2 del 0 plus dot, 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 dot. And what this is doing is sort of taking into account, this one term here is taking into account all possible operators that can form out of the building block phi. So I can think about like a single phi field as being some block, and then I can just multiply lots and lots of them together to make whatever operator I like out of just phi fields, some phi to the power of whatever. And so this is taking care of entering all these into this sum. Okay. Similarly, now you can think about what other building blocks can I use. And so the other building blocks that I have are derivatives acting on phi. So I could consider one of my building blocks, instead of being just the phi field itself, I can consider it being d mu acting on phi. And remember that I'm not worrying about taking Lorentz scalars here, so these mu indices can just be free. And so this term, if I imagine expanding this out, I'll have a term that looks like d mu phi and then d mu phi squared and so on. I can imagine terms with building blocks of 2 derivatives. This notation here sort of means that I take this is the traceless symmetric. This means that they're traceless symmetric, these derivatives. And so that and that's accounting for null conditions in the Hilbert space, or equivalently in a sort of operator language, this accounts for equations of motions. And this general term is a building block that's formed out of n derivatives, again traceless and symmetric, acting on phi. And so each of these terms here comes with some function f. It depends on the space-time dimension, and then this is ft1, ft2, ftn in general. And this sort of tells you the degeneracy of these building blocks. So, for instance, this degeneracy of this building block, this d mu phi, is d, because there are d indices here. And so I could have d mu1, d mu2, up to d mu d. So there are d possibilities here that have this particular weighting of the canonical dimension of phi, delta 0, and then 1 extra dimension coming from the derivative. Now, focusing on the case d is equal to 2, all of these degeneracies are just 2. So it's easy to see that this is just the dimension. It's easy to see that symmetric traceless will give you just two possibilities. You have dx, you can imagine a 2 by 2 matrix with xx, xy is symmetric. So there's sort of three components there, but you remove the trace that reduces to 2. So everything is 2. There's a term here that diverges. We can just ignore this as a sort of regularized thing. It's just the fact that the scalar field is actually has dimension 0 in 2 dimensions. So it's sort of, there's some 0 modes that you need to ignore. And so you can just get rid of that term. And so the partition function looks like this. Now, I can write this in, I can relate this formula, this partition function, to the Dedekind eta function. So this is, again, follows Carly's paper from '86. So the eta function is defined in the following way. And so you can see that this partition function here is just, that you have to make up some factors of this q to the 1/24th here, but it's given by essentially 1 over this Dedekind eta function squared. And we're interested, again, in knowing the beta goes to 0 limit of this, where q is equal to e to the minus beta. So what is the limit of this partition function as you send beta to 0? So clearly, as you send beta to 0, the q is going to 1, and this term just goes to 1 in the numerator. So we have to work out what the limit of beta goes to 0 of this Dedekind eta function is. So in d is equal to 2, there's something very special you can use. Because you've related it to this eta function, you can use the modular property of this eta function. And the modular property takes the following form. It says that the function evaluated at q is equal to the e to the minus beta is equal to this following expression. And see, as you hear, you've pulled out a factor of 1 over square root of beta here. And then you evaluate the eta function where you sort of inverted the beta dependence. There's some factors of pi that make this up in the argument here. And so we can use this property and then look at the beta goes to 0 limit of the right-hand side of this equation. And so clearly, this is going to diverge as 1 over square root of beta. And so what happens to this eta of e to the minus 4 pi squared over beta? Well, so as beta goes to 0 here, this thing is going to go to 0. And so this whole part of the eta function is just going to end up being 1. And you're left with just this q to the 1/24th. So this 24th, so you get this factor raised to the power of 1/24th. And so you see that the eta, as this q tilde now goes to 0, as beta goes to 0, q tilde also goes to 0, looks like this factor here to the power of 1/24th. So you get this. And then the full beta function was 1 over this eta function squared, and this is in q. So you pick up 2 powers of this root 2 pi over beta in the denominator, and so you get that this partition function, as beta goes to 0, it goes like beta, so that goes to 0, and then some exponent that has a 1 over beta dependence with some factors of pi's and 3's. Okay, and then you can then do this inverse Laplace transform to understand how the density of operators grows. And so this density of operators as delta goes to infinity is the inverse Laplace transform of this that we just worked out as beta goes to 0, and it takes the following form. So this tells you how many operators there are at mass dimension delta. This is an asymptotic formula for their growth in 2 space-time dimensions. So that is all very special to d is equal to 2, but I said we wanted to look beyond d is equal to 2. So let's go back to this sort of master formula and look at what happens to this master formula d is equal to 4. So this, now the scalar field has mass dimension 1, and this function is given by a 1 plus k squared. But you cannot relate this partition function to the Dedekind eta function. You cannot use this lovely trick of modular invariance. So what do you do? Well, so you can perform the following manipulations. So this is the partition function that I just had on the slide ago. This next step is just simply a shifting of the sum from k is equal to 0 to k is equal to 1. So it looks like this form. And then I sort of take, I write exponential log of this whole thing. I bring down this k squared and rearrange and expand the log inside the exponential. And that gives me this expression here. I'm substituting in q is equal to e to the minus beta here. And then I can perform a Melian transform on this. And so the Melian transform, I write this e to the minus beta kn in the following way. So there's some contour that I'll specify in a second. And then I substitute this in here. And so you can see here that there's a sum over k. This sum over k is going to give me some zeta functions that appear here. So this sum over k, there's a k squared here, there's a k to the minus s here. This gives me this zeta function of s minus 2. Similarly, there's a sum over n, and that gives me this zeta function here. And then there's a gamma that was in the Melian transform here, and then there's a beta that was in the Melian transform in the first place here. And so I'm just going to very quickly sketch how you can further evaluate this to get out the information that we want about the beta goes to 0 limit. And so now I can define this contour C that you get from the Melian transform. This contour C lies here above this has a pole at s is equal to 3. So you have to take this contour to be to the right of all your poles. And the idea is to sort of move this contour C, move it to somewhere left of the origin and above the point minus 1, to some contour here. And there's a theorem by Meinardus from the 50s that tells you if you do this and you look at the beta goes to 0 limit, then the integral along this line here will be an error term to the asymptotic growth. And so you can sort of close this contour and you pick up the contribution from the residues. And there's a simple pole at the residue of this guy, as s is equal to 3, and this has this residue that looks like this, and there's a double pole at s is equal to 0. And I don't really want to go too much into the details, but this is the expression you get. It just comes from the poles of this thing. And so this partition function for the scalar field in d is equal to 4 as beta goes to 0 takes the following form. And this is exact up to some error terms that don't matter as beta goes to 0. And again, you can take the inverse of the Laplace transform to find this growth of operator densities. This is rho of delta. As this inverse Laplace transform gives you this sort of this expression here. So you see there's an exponential growth in delta in mass dimension. And what I've done in this plot here is I've calculated the exact number of operators at each mass dimension in an EFT of a real scalar field. And then compared it with this result. And remember, this result is supposed to be an asymptotic result. But already you see that there's a thin gray line here that corresponds to this formula here. Already you see it lies right on top of the actual sort of data that you get. And you can see that it starts sort of 10 to the minus 1, or sort of 10% level correct. And then it goes down here, it drops below 1 part per mil. So already, kind of remarkably, this formula for the asymptotic growth is giving you really, really accurate results, even at the sort of lowest mass dimensions. Okay, so that's the kind of technique that gives you a flavor of the kind of the mathematics that we use to prove these results. Let me now give you just a flash up some of the main results from this paper in the last, this is just in the last 5 minutes. And to do these results, what we want to do is to generalize this Meinardus theorem so as to obtain results for arbitrary dimensions, EFTs, and arbitrary dimensions, and for particles with arbitrary spin in EFTs. In particular, we were interested in just trying this for the standard model EFT. We also considered the case where you do project to subsets, so Lorentz or internal symmetry singlets. So again, so that we could apply it to the standard model EFT. Okay, so one of the main results was that we determined the leading behavior, so the leading growth of operators in arbitrary dimensions and arbitrary spin. This is, in fact, our results allow you to do all sub-leading terms, but you can't be completely general. So this is a very concise way of presenting just the leading behavior for the arbitrary case. And that tells you that the log of the h here is either a Hilbert series or the full partition function. As beta goes to 0, gives you, it goes like beta to the d minus 1. So and so there's some factors here. There's a zeta d. This is the factor of the statistics. It depends on whether your field is bosonic or fermionic. And then there's a function here that we identified as the dimension of a particular representation of SOT. But this tells you the leading behavior for arbitrary. This depends on the spin of the particle here. So you can see that the leading behavior is basically just dependent on statistics, and then there's some numerical constant that depends on the spin. And then other than that, it just depends on the space-time. We have a full result that includes order 1 multiplicative factors. So we really get the full asymptotic result. No order 1 terms left over. This is the error as you take the mass dimension to infinity will go to 0. For the case we wrote down a sort of master formula for G0 with arbitrary spin. And so this is what it looks like. So this is the Hilbert series as a function again of beta. As beta goes to 0. So let me start with this term here, the main term, which is the exponential term. You see this leading term here, which again just depended on the space-time dimensions. It's 4, so you get a beta to the -3. And there's some coefficients A, B, C, D. Again, the leading term only depends on the number of bosons and the number of fermions. It's only sensitive to the statistics of your fields. And then there are subleading terms, and we captured all subleading terms down to these log beta terms, which of course then turn into polynomials because it's e to the log beta. If you keep only primary operators, conformal primary operators, this was this idea of only counting the follicle operators, you get a suppression that's polynomial. If you project to Lorentz scalars, you get a suppression that's polynomial. Here, there's a b to the power 15 coming up here. And if you suppress by some gauge singlet, looking for gauge singlets, again, you get a polynomial suppression in this beta. So really, all these sort of suppressions that come from restricting to subspace is a polynomial. The main growth is already determined just by by that full partition function. And so let me, the last sort of slide, show how this works for the EFT of the standard model. So the standard model, these are all the fields, these are all the representations they're in. You can stick these representations into the master formula. This dmg here is the dimension of the gauge group. And you can just work out how many fermions you have, how many degrees of freedom are bosonic. And put this into the master formula and then do the inverse Laplace transform. This now I've kept the number of generations in the standard model to be some free parameter here, ng. And so this is the growth of operators that you get. So there's an exponential growth that goes like this delta to the 3/4. And then there's some subleading terms here. This is the exact sort of order 1. This zeta prime term came out of this Maenardus result. It was sort of taking this, I briefly sketched how you take the pole is coming from the residue at 0. And then there's some numerical constant here. This is some order 1 number exact. Okay. And so this is just plotting these results. The last 2 slides I skipped over were just a slight talking about how you can capture some subleading terms, and that's denoted by the fact that these deltas have a slight tilde over them. They're slightly shifted to capture some of the subleading terms. And we see that these asymptotic formulas, again, even at the very low mass dimensions, we can only calculate up to about mass dimension 20, 21, 22 or something here. But even at these very, very low mass dimensions, a very complicated EFT, these asymptotic formulas should only really work, or only have 0 error as delta goes to infinity. Really they go right through these curves. It's kind of remarkable. When I started this project, I had no idea that one would end up with such funky formulas. I never thought I'd write down a formula like this in my life. Or 2, that we would have such good agreement at low mass dimension. So that's kind of interesting in itself. Okay, so with this, we determined the growth of operators in the standard model EFT. And so let me just leave you now, as I've definitely run out of time, let me leave you with some closing thoughts. So I think the main takeaway from this talk is, certainly from the second half of this talk, is that it's developed as this new tool was also used in the first half to systematically count operators that were for LAC Pheno. But there's a new tool in the analytic study of EFT. And so there are a number of ways in which we are further investigating its use. One thing that I'm interested in studying is the operators give you some basis in which to expand observables. And so this result on how the dimension of that basis is growing must give you, at least naively gives you, some insight into how the coefficients that multiply each of these basis terms must, in some average sense, how they must be suppressed in order for some function that discloses observables to converge. And this kind of relates to similar studies that study the rate of convergence of the OPE in CFTs. I'm interested in whether it can provide any useful input to the S-matrix bootstrap program. And then there's this idea of whether you can use these techniques to look or to investigate dualities, new types of dualities, like the types of dualities you can check in ADS CFT entropy checks. And as a final thing to say, a kind of operational point, even though we're seeing this sort of 10 to the minus 3 level precision, we suspect that one can do even better than this and potentially much, much better. So for instance, there are very similar kind of partition functions in the literature that's in mathematics literature that are studied under the name of super asymptotics. This is sort of finding optimal points in which to keep sub-leading terms in your asymptotic expansion. At some point it will diverge, but there's a sort of sense in which you can choose an optimal point, and there they find things like 300 digits of agreement with the exact results. And so there, one could even turn it into a tool for calculating the actual exact numbers, because if you have 300 digits and you have some number 0.00000001 or whatever, you assume that the integer number is correct. Okay, so let me finish with those thoughts. So thanks for your attention. And I can take questions.
Thank you, Tom, for a very impressive talk. And I think we'll have time for questions. Please raise your hand or just unmute yourself and ask the question. All right, maybe I'll start, Tom. Asking questions. So, look, it's very impressive, but I'm not quite clear about the practical applications. Maybe you tell us about more concretely what kind of dualities, for example, you envisage to get from these formulas.
Yeah, so I mean, I'd be happy to discuss that with you, like maybe offline after this, if there is a time for discussion. These are these are ideas that we're just currently pursuing, but they in a similar kind of vein to the ADS CFT. Looking at the entropy of the CFT, the high temperature, the growth of states, the growth of the entropy, and then comparing that to calculations in some gravity theory. Now, which gravity theory one should do the calculations for, and which theories we should apply our techniques for, that's the kind of interesting question, and whether one looks for supersymmetric theories or somewhere else. Whether one can look for sort of, there's literature on large, if you can include sort of large n limits into this as well, there's some literature on that too. But yeah, these are sort of ideas that are forming, and yeah.
Okay. Yeah. So are there any other questions from the audience? Maybe what we do, we'll stop now recording, and everyone wants to stay with Tom and discuss this offline, we'll continue discussion. We are very welcome, but otherwise we'll kind of stop, official part of the webinar. Okay.
Yeah.
So